Welcome. In this video, we are going to talk through some redox reactions, and we're going to look at representing balanced redox reactions using half reactions. So we're going to think of those two things that happen during a redox reaction. Excuse me, there you go. the redox, the read stands for reduction, and the ox stands for oxidation. And we're going to think of those. We're just going to take these redox reactions and kind of show them as the two separate components happening. We're going to show the reduction half and the oxidation half. And these are what we refer to as half reactions. And there's a video going over the basics of this, like what do we mean by half reactions. This video is just going to talk through some sample problems. So if you haven't watched that first video yet, or haven't looked at the notes yet on redox reactions, half reactions, look over that one first. All right, so let's do a quick review of what reduction and oxidation is. So remember, there's a couple tricks we have to remember what it means to be reduced or oxidized. One of those tricks is oil rig, and that means oxidation is loss. So in oxidation, you lose electrons. Reduction is gain. So in reduction, you gain electrons. So these redox reactions involve a transfer of electrons, and one element's going to lose electrons, another one's going to gain electrons. So let's look at some of these reactions down here. So in this first one, we are given a balanced chemical equation. This is what we call the molecular equation. And first thing we're going to do is we're going to write it as a net ionic equation. For our molecular equation, this is representing everything as molecules, which is not accurate because we know that ionic compounds such as chromium chloride, when they dissolve in water, they're actually going to split apart into ions. So we know that these aqueous things, like our chromium chloride and also our hydrochloric acid, our acids will also split into ions. They're going to split apart in ions. So let's write it that way. So chromium solid, it's a solid, so it's not going to split into ions. But our aqueous hydrochloric acid, when it dissolves, it's going to break apart into, whoops, I forgot the two there, into these ions, 2 hydrogen ions and 2 chloride ions. And then over here, your chromium chloride is going to break apart into these ions. If we don't know the charge of chromium, notice how it took 2 chlorides to bond with 1 chromium. So we can figure out that our chromium must have a charge of +2 by, deducing that there. And then hydrogen is a gas. So I'm not going to ionize anything that's a gas or solid or liquid. I'm only ionizing my aqueous things. And then I look for things that are spectators. So in this case, my chloride ion's a spectator. Notice how its oxidation number is not changing. It's an aqueous Cl- ion on both sides of the reaction. So it's what we call a spectator. So the net ionic equation is this right here. So you have some solid chromium interacting with some hydrogen ions. And as a result, we get chromium ions and hydrogen gas. So remember the oxidation means losing electrons. And reduction means gaining electrons. So what we want to do is we want to take this overall reaction and try and show it as the two separate things that are happening, the oxidation half and the reduction half. So to figure out who's being oxidized and who's being reduced, we can determine the oxidation numbers of everything involved here. So if we look at our oxidation number rules, which again, there's another note sheet in the video talking about how to find oxidation numbers. So go back and review that if you're unsure about that. But based on our oxidation number rules, if you have like a solid, something in its elemental state, so like pure solid chromium that's in its elemental state, it has an oxidation number of 0. If something is an ion, the oxidation number is the same as its charge. So hydrogen has an oxidation number of +1. Over here, we got another ion, so the oxidation number is going to be the same as its charge, so it's +2. And then hydrogen gas, this is hydrogen in its elemental state, so it has an oxidation number of 0. Just make a little note there at the top. So oxidation means losing electrons. So which element is becoming more positive, right? Because if you lose electrons, you're losing negative things. So you're going to become more positive. It looks like my chromium is the one that's becoming more positive. Chromium is going from oxidation number of 0 to an oxidation number of +2. So to show completely what's happening, so chromium is going from 0 to +2, and what happened in order to go from 0 to +2 is it lost 2 electrons. So we're going to show the 2 electrons being on the right side because it's like my chromium is split apart into the chromium ion plus 2 electrons. So this chromium, like, gave up 2 electrons, leaving behind the chromium plus 2 ion. So this is how we would show an oxidation half reaction. You will notice in an oxidation reaction, you see that the electrons are the product, right? Because it's giving up electrons, so it's kind of like it's producing electrons. So the electron's always going to be on the right-hand side of an oxidation half reaction. So in our reduction half reaction, we should see the opposite thing happening. So who's being reduced? Well, it looks like our hydrogen ions are going from a positive to a positive oxidation number to an oxidation number of 0. And if we're trying to figure out, well, how many electrons are gained or lost, well, there's kind of 2 different ways to think of it. One way you can think of it is we've discussed earlier that reactions have to be balanced for both mass and charge. So being balanced for mass means, oh, look, I have 2 hydrogens on this side, I have 2 hydrogens on this side. That's what we mean when we say it's balanced by mass. When we look at balanced by charge, let's look at this example up here. Notice how on the left, your chromium has a charge of 0, it's neutral. Over here on the right, you've got a +2 ion and you've got 2 negative electrons. So the charge on the right is also 0. So that's what we mean when we say it's balanced by mass and also balanced by charge. So we say something's balanced by charge means the charge on the left-hand side is equal to the charge on the right-hand side. So if we look down here at this second example, notice how the charge on the right is currently 0 because this is neutral. And then on the left, you have 2 positive hydrogens. So the charge on the left is currently +2. So if we want to make sure the charge on the left is equal to the charge on the right, the only way we can do that is we can add 2 electrons over here. So now, notice I have 2 negatives and 2 positives. So now the charge on the left is 0, and the charge on the right is also 0. So that is what we call our balanced half reaction. It's balanced for mass. We've got 2 hydrogens on the left, 2 hydrogens on the right, and it's balanced for charge because the charge on the left is 0 and the charge on the right is 0. And the other thing we'll notice is we're comparing like the overall equation to these half reactions. A couple things we want to notice is that in an oxidation, the electrons are being produced. In a reduction, the electrons are being used up. So oxidation, the electrons show up on the right. In a reduction, the electrons show up on the left. The other thing we should notice is that the electrons gained in my reduction is equal to the electrons lost in my oxidation. So that's it's basically an example of the law of conservation of matter. So electrons cannot, appear or disappear. So however many electrons you gain must be equal to the number of electrons you lose. So that's an important thing to be aware of. So the number of electrons transferred in this reaction, that might be something you'd be asked about. You'd say, oh, we're transferring 2 electrons total. And what that means like you're transferring 2 moles of electron per reaction, that occurs here. So let's look at another. 2 is similar to 1. And then let's look at an example where you are adding up the reactions instead. So let's look at this one. So let's do this one right here. So we're looking at copper and nitrate, and this is actually something that was happening when we dissolved that copper penny in nitric acid. There's actually a redox reaction that was occurring, so that we're going to actually represent right here. And you might remember we made that brown gas. That was our NO2 gas that we made in the fume hood. So for those of you who remember doing that brass lab, we were observing this reaction occurring. So first, let's look at our oxidation numbers. So if it's an ion, the oxidation number is the same as the charge, so copper's +2. If it's in its elemental state, like the solid copper over here, oxidation number is 0. So it looks like copper is being oxidized because its oxidation number is going from 0 to +2. So since the charge is becoming more positive, that's an indication that it's losing electrons. Remember, electrons are negative. All right, so now let's look at who's being reduced. If you're looking at your oxidation numbers here, this one's a little more complicated to work through. So going through our oxidation numbers, we know hydrogen's +1 because it's an ion. And then our nitrate, let's break this one down. We don't have a rule regarding nitrogen, but we do know that oxygens tend to be -2. So I've got 3 oxygens, they're each -2. And we know that overall, this thing has a charge of -1. So my 1 nitrogen and my 3 oxygens, those numbers need to add up to -1. So the only way that works out is if my nitrogen is +5. So you see I'll have a +5 oxidation number and a -6 oxidation number add up to -1. So that's how I'd figure out my nitrogen. Okay, now let's go over to this side. Remember, oxygen is -2 when it's in a compound. So I've got 2 oxygens here. Overall, this compound is neutral. So that means my nitrogen on this side has an oxidation number +4. Let's look over here. My oxygen's -2. My hydrogens, whoops, there's only one of them. And then my hydrogens are typically +1 when they're bonded to a nonmetal. So that works out there. So if we look whose oxidation number is changing, it's nitrogen. And nitrogen's going from +5 to +4. So since it's becoming, less positive, that means it must have gained something negative. So it gained an electron. So that's why it's being reduced. And in order for my overall equation to work out, my electrons gained need to equal my electrons lost. So I'm going to go back here. I'm going to erase some of this because it's kind of a mess. And here we go. So right now, each copper atom is losing 2 electrons, but each nitrogen is only gaining 1 electron. So in order to have these add up to make a balanced overall reaction, I need to be gaining 2 electrons as well as losing 2 electrons. So what I'm going to do on the bottom here is I'm going to take this whole equation and I'm going to multiply it by 2. So what I end up with is, let me write this out. My copper reaction does not change. Whoops. Hold on, there we go. So here's my copper reaction. Notice how it's an oxidation. So the electron is over here on the right because it's giving up electrons. My second one is the reduction. So I'm going to double everything. So it's going to be 4 hydrogens and 2 nitrates and 2 electrons on the left. And then over here on the right, what we're producing is 2 nitrogen dioxides and 2 waters. And then I'm going to add these up the same way you might, add up reactions when you're doing like algebra. You might add up equations. I think is a similar process here. So I'm going to add them up, add up whatever's on the left. So on the left, I have copper and 4 hydrogen ions and 2 nitrate ions and 2 electrons. And then over here on the right, I've got a copper ion. I've got 2 electrons. I've got 2 nitrogen oxides and then 2 waters. And I'm getting lazy and not labeling the states of matter here on these ones, but here we go. And then I look for things that are the same on the left and right, things that might cancel out. So my electrons should cancel out. So I got 2 electrons on the left, 2 electrons on the right. If I've done everything correct, that's what I should see. My electrons gained should equal my electrons lost. So my balanced overall equation should not have electrons showing up in it, because electrons gained equal electrons lost. And then double check nothing else is like a spectator. So this is my overall equation. I've got my solid copper and some hydrogen ions and some nitrate ions forming copper ions, and then some nitrogen dioxide gas, and then 2 liquid waters. So again, this is the reaction we saw if you have seen like either copper cycle lab or like the dissolving of brass or dissolving of a penny. You have copper that dissolves in nitric acid. This is what's going on there. It's actually a redox reaction that is occurring. So there we go. So there's a fully, worked out answers for the other problems that you can check as well. And let me know if you have any questions.